So one of the last things as far as Faraday's law goes in chapter 30 to talk about is when an induced EMF is present, how does that affect an electric field? All right, so what we have here is a wire loop of some radius r, it's circular. It's a conducting wire loop, but the charges aren't necessarily initially in motion, right? Say they're at rest initially. The external magnetic field as shown points into the page, so there is some magnetic flux. And let's just assume for our purposes now that that flux is decreasing in magnitude in time. Okay, so same direction, the same area. The strength of this magnetic field is just getting weaker and weaker. Thus, there's an EMF. Whoops. Let's do that one. There's an EMF induced in that loop that's equal to this, right? Okay. Now, we have an electric field present, right? This is something new. I haven't mentioned this before yet. At every point in this loop or on this circle, on the charges, there is an electric field that arises because this EMF is doing work to move those charges around the loop. And because charges are in motion, that's effectively a current. That means we also have an electric field in the direction of their motion. And there are just 4 locations that the electric field is being specified here, but really there's an electric field at every point around this loop. Okay, every single point, but just 4 are shown for simplicity. So if that magnetic field is decreasing, the flux is decreasing, there's an induced current and an induced field that tries to increase the flux again back to what it was, right? It wants to resist that change. So which way does that have to be? Well, if that flux shown is decreasing, the induced field, I'll write it in blue, that has to go in the opposite direction, right? It wants to increase it again back to what it was. Right? So that field is, well, out of the page, which creates an induced current counterclockwise. And so for each of those 4 points shown, there's the current vector in those same directions. Right? So E and I are in the same direction. And so you can kind of think of this as an induced electric field, right? But that's all due to the fact that the magnetic field, or rather the flux, is changing. So this also, this also induces an EMF, which remember is another way to write a voltage source in this case. It's an induced voltage. And so we write that as such. It's the closed integral of the electric field dotted with the path length, ds. In this case, it'll be, 2 pi r, but in any case, as long as that loop or that path is closed, we will have this closed integral be true. Okay, so that's a separate way to write the induced EMF. Because they're the same, we can equate these two, right? They're the same thing. So the induced EMF is equal to that expression, right? That closed integral. And it's also equal to negative the change in magnetic field. And so this is a direct way to relate the electric field and the magnetic field, right? Remember that the areas have to be closed. It has to be a closed loop. That's why I have the closed symbol on each of these integrals there. Okay, if it's not closed, then this does not apply. The reason that there kind of is an electric field, or rather a hint as to the fact that there is an electric field in the first place, is if you think of these charges initially at rest, how do they get in motion? Well, there has to be some force on them, right? If you do the magnetic force, right, that is QV cross B, that means by the right-hand rule, if we put QV, say we choose a point that direction, B is into the page, that means that the force is leftward. Okay? But that's not the force that initially gets them in motion, right? Because the force is, well, to the left. There's a force in the direction of the electric field. What force is that? It's the electric force. QE, right? So this brings up what's called the Lorentz force. We can write it like this. Well, let me just write it like this. It's simply the sum of both electric and magnetic forces. That's it. All right, this is the Lorentz force. We'll see this come up later in later chapters, chapter 32, and you'll see it come up in 4C. But this is effectively the total force on a charge moving in a closed loop subject to an electric field and a magnetic field. And it comes back to the fact that both of these are induced from the fact that the magnetic flux is changing in time.